Hello everyone, I'm Jo from Korea University. Now I present a paper titled Cryptbara Dependency Guided Detection of Python Cryptographic API Misuses. Modern software depends on cryptography to protect confidentiality, integrity, and authenticity. Crypto API misuse is a major source of security vulnerabilities. These examples look syntactically fine. The developer uses the correct API, but the settings are weak, and this still leads to real security bugs. In Python, dynamic features make risky pattern more common and harder to spot. We face two core challenges. First, syntactic ambiguity. Even when the syntax is correct, critical values may be defined far from the actual API call. In this example, the iterations used in PBKDF2 HMAC is actually coming from another helper function. So if we only look at the call site, we have no idea what value is being used. And the same method name like update can mean different things depending on the object. For example, cipher update and hash update have totally different behavior. So we need to trace beyond the call site to understand what really reaches the crypto API. Second, semantic ambiguity. The code can look fine, but safety depends on policy and intent. Here, get key may return a default key instead of a derived one, and that choice is not visible from syntax alone. Our motivation is simple: make LLM see the context, not just the line. LLMs alone can't handle Python's ambiguity, accuracy drops. We extract structure dependency information to feed it to the model. This resolves syntactic ambiguity and enables semantic judgment so the LLM can decide misuses, not guesses. So we propose Cryptbara, a dependency-guided LLM for precise Python crypto API misuse detection. It works in two phases. In phase one, we perform static analysis to recover required dependency. And in phase two, the LLM makes a judgment based on the relevant information. In phase one, we run static dependency analysis. We extract each crypto API's context at intra and interscopes. Inside a function, we capture three things: who calls the API, where the return value goes, and the in-function call order. This example shows how we identify the receiver. The call site is line 5, cipher encrypt. We run a backward slice to the last assignment on line 4, so the receiver resolves to cipher. And the return value, we run a one hop for a slice from the API call to see where its output goes. In this code, the result flows into encrypted data and is returned on line 6. If it were stored or passed as an argument, we'd record that next hop instead. Third, call hierarchy. We scan within the function to list direct callers of the function containing the crypto API. In this example, handle request calls encrypt data. We record the caller name, call site line, and passed arguments. This tells us who triggers the API and sees next phase tracking. Across functions, we record parameter flows to the API, which hard-coded literals feed which arguments, and the end-to-end call chain from entry to the API site. Now, parameter propagation, we run an AEST backtrace at each call site, then follow caller calling links to rebuild the cross-function flow. The password flows from handler request through derived key into the key, and finally into encrypt. We record each hop so the model sees exactly what reaches the crypto API. Next, constant uses. We scan call site leaders, map them to API arguments. Here, the salt on line 4 becomes the salt parameter of PBKTF2 HMAC on line 8, and the 10,000 is the iteration count. Lastly, the call chain. We expand the call graph from entry points and list the end-to-end path to the API side. In this code, the passes handle requests to graph_key, to encrypt data, to cipher.encrypt. Next, phase 2, we use structured rules and static dependency to bound the LLM's reasoning. Inputs are three things: the target code, the selected rule, and the dependencies. The model answers only within that rule scope. Next, our rule set, rules based on documents tightly bound the LLM's decisions and the results. We evaluate on two datasets. First, PyCryptoBench, a public set of labeled crypto code. Second, a real-world dataset we created. We compare against Ligma and Cryptolation. On PyCryptoBench, Cryptbara gets F1 score of 95.43. On the real-world set, it reaches F1 score of 84. Next, why it works. First, the prompt. We include the security rule and the dependency facts. Then we run chain of thought. That change alone boosts recall by 25 points and F1 by 11.6. Second, the backend. We tested multiple models. GPT-4 or Mini works best with an F1 score of 95.4%, recall of 97.9%, and precision of 93.1%. In practice, we scanned large GitHub repositories. We found 172 potential misuses across 34 repositories. We reported 22 cases. Python crypto API misuse is context dependent. Cryptbara combines static dependency analysis with rule-guided LLM prompts to detect Python crypto API misuse accurately. It outperforms state-of-the-art tools and revealed 172 previously unknown misuses. Cryptbara contributes to safer and more consistent use of cryptographic libraries. Thank you for your attention.